In recent years, scientists have recorded deep seismic signals beneath the Pacific that do not behave like those from solid rock. The patterns are still under investigation, but some resemble the echoes that can form in large underground cavities. Such anomalies often prompt follow-up expeditions, much like the documented extreme cave dives and trench explorations that have revealed environments once thought impossible for life. Coupled with accelerating advances in radar mapping and subterranean surveying, these findings are drawing mainstream attention to the planet's unexplored depths. And in early 2025, one global report would show just how far that exploration had advanced. The 2025 boom in underground exploration. By the start of 2025, researchers and exploration groups were documenting an unusually sharp rise in successful cave surveys, deep mining reconnaissance, and subsurface mapping. The growth wasn't confined to one country or driven by a single discovery. It reflected a combination of factors. Industry reports on the global cave diving market showed a marked increase in expeditions being planned and funded, while coverage in specialist outlets like Shearwater noted a swelling community of technical divers and speleologists exchanging data more fluidly than ever before. Advancements in sensing equipment, particularly compact, multi-channel arrays and drone-mounted ground-penetrating radar, were shortening the time needed to produce usable maps, even in difficult conditions. These systems, developed for rugged or hazardous terrain, were deployed from deserts to polar ice, operating where human access had once been slow or risky. Part of this surge came from the deliberate coordination between national surveys, academic labs, and private operators. In earlier years, valuable subsurface data often sat in separate databases or paper archives, making broad comparisons difficult. By 2025, shared platforms and standards meant that data from a Greenland ice cave scan could be cross-referenced with karst system imagery from central Mexico, sometimes revealing structural parallels that would have gone unnoticed. Field crews equipped with imaging units small enough to fit in a backpack could send three-dimensional models in real time to off-site analysts, who then advised on which passages merited direct exploration. This approach not only reduced the likelihood of bypassing concealed voids behind collapses or fissures, it allowed for rapid reallocation of resources when conditions changed. Several documented field projects stood out, both for their difficulty and for the insights they offered. The BBC covered J2 cave descents in Mexico, in which technical dive teams led by Phil Short reached submerged chambers far deeper than conditions had suggested possible, provided a rare look at flooded systems with complex hydrology. Meanwhile, National Geographic's expeditions into Greenland's Wolfland ice caves revealed melt-carved interiors so extensive that internal acoustic mapping was needed to plot their extent. In both cases, the discoveries upset earlier assumptions about how such environments evolve, forcing model revisions about climate, water movement, and structural stability beneath ice or mountains. These were representative of the kind of fully documented surprises now emerging each season. As the datasets from these and other expeditions grew, so did efforts to link field results with broader geophysical measurements. Recent seismology research, including new modeling ideas from studies of Earth's deep interior, has encouraged teams to examine whether certain low-frequency or damped seismic patterns correlate with the locations of mapped cavities. While this is still an open question and not yet a proven mapping method, targeted surveys informed by seismic clues have shown promise in focusing searches. In a few cases, ground-penetrating radar crews were dispatched to sites earmarked by these patterns, and they returned with usable maps of voids matching the rough scale suggested by the seismic interpretation. The work is iterative, and the scientific community is careful to stress that many anomalies turn out to have unrelated causes. Yet the potential for integrating the two approaches is driving active collaboration between seismologists and cave surveyors. The same link between technology and strategy is changing how expeditions are planned. Instead of evenly distributing effort across large, unmapped areas, modern teams increasingly prioritize places where multiple lines of evidence converge. Historic reports of unusual subsurface formations, unexplained density readings, or subtle anomalies in long-term seismic monitoring. Where older campaigns might spend weeks clearing collapsed entrances or probing dead ends, project leads now arrive with layers of preliminary data hinting at which directions hold the greatest promise. This has already produced a series of efficient, high-yield missions in Europe, the Americas, and Asia, where networks of passages were charted in a fraction of the time earlier techniques required. Underlying these rapid gains is a gradual shift in how subterranean environments are understood. For decades, geologists regarded large, stable voids in the crust as exceptional and largely confined to specific geological contexts. The accumulation of new maps, whether from ice, volcanic rock, or sedimentary formations, suggests such structures may be more common and diverse in origin than assumed. Some seem to align with known fault lines or remnants of ancient volcanic plumbing. Others have no obvious link to local tectonic history. The emerging picture is less one of uniformity and more of a varied subsurface terrain, where both slow geological processes and sudden events leave behind complex architecture. These insights are not just of academic interest. Knowing the distribution and character of large voids has applications in resource planning, environmental monitoring, and hazard assessment. In water-scarce regions, for example, enclosed cavities can serve as reservoirs or influence groundwater movement. In others, their stability or instability can affect building safety and land use. Because of this, there's growing interest in establishing more complete catalogues that record each mapped void size, depth, and environmental conditions. Such a record would be invaluable for comparing patterns across continents and for testing hypotheses about their formation and longevity. Even with the acceleration in mapping, researchers acknowledge that what is now visible may be only a fraction of what exists. New tools reveal more in the areas that are actively surveyed, but large portions of the planet's interior remain logistically out of reach. Efforts are underway to adapt aerial and orbital sensing, already proven in archaeology and geology on the surface, to detect indirect signs of subsurface architecture on regional scales. Combining such data with on-the-ground verification could, in the future, greatly expand the known map without requiring exhaustive manual exploration in every location. What unites the events of 2025 is this intertwining of technological capacity and cooperative networks. The pace of mapping has increased where these conditions overlap, and the information gathered has begun to refine not just where further exploration should occur, but why certain formations appear where they do. In this growing body of evidence, physical measurement meets interpretation, and interpretation sometimes reopens questions that seemed long settled. Occasionally, these questions extend beyond geology into other domains, raising the possibility that observations made centuries ago, recorded for entirely different reasons, might now be examined under a new light. When ancient myths sound like geological reports. Among the expanding troves of subterranean survey data, a smaller but no less intriguing trend has been emerging: comparisons between physical cave environments and descriptions preserved in oral or written traditions. In 2025, this line of inquiry began to take on a more systematic character, with researchers compiling multilingual myth archives and cross-referencing them against geological records. The question wasn't whether myths were literal maps, but whether some carried enough consistent environmental detail to serve as mnemonic guides to specific types of underground terrain. One of the most discussed examples involved National Geographic's documentation of Greenland's Wolf Land ice caves. In addition to their striking interiors, the caves yielded speleothems whose chemical composition captured paleoclimate records stretching back thousands of years. For glaciologists, this was hard evidence that enclosed subterranean environments had long stored clues about surface conditions. For anthropologists, it suggested a possibility that ancient inhabitants, aware of such environmental constants, may have encoded their knowledge in descriptions that survived as oral accounts. A description of skyless halls where the air carried the taste of cold stone, for example, might match what a traveler encounters inside such an ice cave, and the environmental markers, darkness, unchanging chill, the soundscape, could persist across generations of retelling. Archaeologists familiar with similar phenomena in other regions began revisiting long-dismissed refuge stories. In South America's Andean highlands, several communities maintain origin accounts that include moving into the earth during a period of unlivable surface conditions. The details vary, but some narratives specify extended movement through enclosed spaces and an auditory shift described as the outside gone silent. These are not proof of any one event, but offer details that can be tested. Using low-frequency ground-penetrating radar and portable gravimeters, equipment now compact enough for remote use, survey teams can quickly determine whether voids exist near the locations named in the stories. Findings are uneven, but in a few tested sites, geological signatures consistent with substantial underground cavities have been recorded, prompting further exploratory proposals. The database approach marks a shift away from relying on singular, sensational finds toward broader pattern analysis. Folk traditions from Central Asia, for instance, often speak of inclined passages beneath mountains, leading to spacious chambers where communities weathered long winters. While such accounts are common in highland cultures, recent karst surveys in select parts of the Tian Shan have documented deep fracture-linked voids large enough to accommodate groups of people. The surveys don't prove habitation, but they demonstrate that the environmental setting described does physically exist in those regions, making the oral accounts at least geographically plausible. With mythic references logged in a searchable format alongside modern geological data, such overlaps are easier to flag without overextending the claims. A similar care has been applied to Pacific Island traditions. On some volcanic islands, accounts speak of stone corridors, allowing inland passage during severe coastal flooding. Radar imaging on one island's interior mapped a collapsed lava tube, whose seaward opening may once have offered such a route. No one can say for certain whether it is the exact feature in the story, but the alignment between geological structure and narrative outline has been sufficient to place the site on the list for careful documentation. In this way, the process treats myths as prompts for investigation, not conclusive evidence. One of the practical strengths of this method lies in its scalability. With many myths now digitized and indexed by environmental keyword, terms like heat from the floor, perpetual night, or water without wind, searches can be run against the growing registry of subsurface anomalies. When a story's described features cluster in a region where geophysical surveys have revealed cavities, that region can be prioritized for non-invasive study. This approach has already influenced where scarce survey resources were deployed in 2025, sometimes in parallel with other drivers such as conservation goals or mineral assessments, keeping work efficient and multi-purpose. The idea of myths preserving survival knowledge is not new, but what changes the discussion now is the ability to directly test the fit between story and site. Low-frequency imaging can distinguish between dense rock and open space even at depth, while gravimetric readings can signal density changes suggesting a large void. These data streams, when aligned with persistent mythic descriptions, have sometimes led to fieldwork whose results validate at least the geological plausibility of the narratives. Among the small successes this year was a site where such combined cues led to the detection of a lateral tunnel ending in a larger cavity. The space remains partly blocked by debris, but its scale is consistent with the type of shelter described in the related account. Even when surveys return no structural match, the exercise has value. Disproving a specific link refines the dataset, helping to distinguish between recurrent symbolic motifs and those with a stronger environmental basis. Over time, patterns may emerge showing that myths from regions with certain geological conditions more often reference features testable in the field. This in itself could inform future field planning or heritage preservation decisions. From a broader anthropological viewpoint, considering these narratives as functional memory tools offers a plausible bridge between cultural tradition and empirical science. In societies without widespread literacy, memorable imagery was essential for transmitting practical information. The conceptualization of certain caves, lava tubes, or glacier tunnels as guarded underworlds or sacred chambers could have served as a way to ensure the knowledge of their location and qualities endured. Stripped of literal supernatural interpretation, these descriptions can still function as geographic markers, if one knows how to decode them. Greenland's Wolfland findings help ground this perspective, because they demonstrate how stable subterranean environments can archive environmental evidence over vast timescales. If ancient observers recognized even a fraction of that stability, through unchanging air, constant temperature, or permanent darkness, they could have woven these constants into stories that lasted generations. That insight reframes some myths not as hazy allegories, but as cultural packaging for very specific environmental encounters, ones that can now be compared directly with mapped sites. This line of research remains cautious, and for good reason. Many myths will never correspond neatly to a physical location, and many anomalies will turn out to have no connection to historical accounts. Yet the overlaps that do occur are sufficient to keep the collaboration between geologists, archaeologists, and folklorists active. For each potential match, the sequence is methodical. Log the account, note the described features, check for known structures, and if warranted, schedule survey work. In balancing respect for cultural heritage with technical investigation, the process builds a framework where neither discipline claims more certainty than the evidence supports. Increasingly, this multidisciplinary approach is prompting specialists to re-evaluate long-standing material in their own archives. Stories dismissed decades ago for lack of proof are being reconsidered now that tools can probe far deeper and with greater resolution than before. Maps, seismographs, and radar returns feed into the same databases as transcribed accounts, allowing for connections no single researcher could spot in isolation. Over time, clusters of data points, mythic and geological, begin to take shape, offering possible explanations for why certain descriptions are so persistent in specific landscapes. For those working at the intersection of myth and geology, the greatest value is not in confirming or denying individual tales, but in building a shared investigative map of the underground. Each recorded correlation improves the odds of making the next one more efficiently, and each null result tightens the focus of the search. What is taking shape is an iterative cycle. Tradition inspires survey, survey refines tradition's context, and both feed back into a larger picture of how humans have interacted with the planet's hidden structures. Having this growing set of environmental clues, whether drawn from present-day maps or centuries-old narratives, inevitably shapes where eyes and instruments turn next. In some cases, those targets are in terrains relatively easy to reach. In others, the areas of interest lie well beyond the range of direct human access, where researchers must rely on indirect readings and specialized instruments to detect what cannot yet be approached. And it is in those harder-to-reach layers of the Earth where some of the most perplexing signals have begun to emerge. Seismic echoes from the unreachable depths. Earlier this year, a network of deep-ocean seismic stations, set up to monitor long-term tectonic trends, logged a sequence of low-frequency waveforms unlike the typical signatures of earthquakes or volcanic tremors. The station that first recorded them operates in one of the most geologically quiet oceanic zones, positioned far from major plate boundaries and isolated from surface vibration sources such as shipping lanes. The initial readout showed a drawn-out, rhythmic reverberation rather than a sharp jolt, and its slow pulse rate placed it outside the range of most shallow seismic disturbances. Technicians verified within hours that the anomaly was not the result of instrument malfunction, and the data was flagged for broader scientific review. Once the signal was processed using high-resolution analyses, patterns emerged within the waveform that differed from those produced by known deep mantle activity. Certain bands of frequency weakened noticeably when the waves would be expected to pass through particular depth ranges, then resumed strength in lower layers. This pattern did not point to a single explanation. In current geophysics, such changes can be consistent with variations in density, complex layering, or even pockets of partially molten rock. These conditions can alter wave speed or direction in ways that may superficially resemble the effect of a void, But researchers emphasize that identifying true cavities at great depth remains extremely difficult. Anomalies like these are not unknown, but they are easy to lose in the constant background of seismic noise produced by thousands of simultaneous events worldwide. In the past, energy from waves traveling through the deep earth was often masked by unrelated disturbances in the crust or shallow mantle. The difference now is the availability of enhanced signal processing techniques that can isolate fainter, deeper components with much greater accuracy. By compensating for energy loss at different depths and filtering out surface and near-surface vibrations, analysts can reconstruct a clearer picture of how waves behave as they traverse the planet's interior. In this case, the refined data hinted at a zone with properties deviating from surrounding rock, possibly less dense or more fractured, but without definitive shape or size. The variations did not persist for the multi-minute spans that would imply an enormous empty chamber, as such effects remain unconfirmed in peer-reviewed studies. Instead, the measurements suggested a localized region influencing the wave paths enough to merit additional scrutiny. Within the community, interpretations ranged from small-scale heterogeneities formed by past geological processes, to pockets of partially molten materials, to unusual mineral distributions that slow and scatter seismic waves differently than expected. Debate over what these readings represent is informed by other recent developments in seismology. For example, studies led by John Vidal and colleagues have used precise measurements of seismic wave arrival times to propose that Earth's inner core may alter its rotation speed relative to the mantle and crust over decades. That conclusion would have been hard to sustain a generation ago, before high-density seismic networks and advanced timing algorithms made such subtle changes detectable. The same principle applies here. Carefully analyzed anomalies can reveal internal complexity far beyond the simple concentric shell models still common in diagrams. Not everyone is ready to assign this year's deep ocean signal to an unusual geological structure. Alternate interpretations note that temperature gradients or compositional shifts within mantle rock can produce very similar effects on waveforms, without requiring the presence of low-density pockets. Others warn that even with improved filtering, rare noise combinations can mimic the signature of deep anomalies. Still, most agree that repeated detection from multiple stations strengthens the case for a persistent feature in the broad region of interest. In fact, similar wave behaviors were recorded from another part of the same ocean basin network weeks later, prompting targeted follow-up. One reason the location attracts attention is its apparent distance from present-day volcanic ridges, subduction zones, or other deep crust activity centers. These quieter environments are often selected for baseline measurements precisely because they allow subtle anomalies to stand out. So detecting one here raises the possibility of features unrelated to current tectonic processes. Some geologists suggest that the site could preserve remnants of early mantle structures, material boundaries or mineralogical transitions locked in place billions of years ago, that happen to affect seismic waves more strongly than their surroundings. The tools for studying such features are evolving rapidly. Machine learning systems, trained on massive datasets of catalogued seismic events, can now flag departures from expected patterns as they occur, sometimes reconstructing likely source geometries before human analysts have reviewed the data. By running the deep ocean anomaly through these models, researchers can simulate how it would appear if detected by stations placed at other angles or distances. These synthetic perspectives help to refine estimates of the feature's extent and orientation without immediate need for physical instruments in those locations. In trials, such modeling has indicated that the zone in question could cover a larger stretch than early calculations implied, although the resolution is still too coarse for firm conclusions. Part of what makes anomalies worth tracking is their potential to refine theories about how a planet's interior works on both short and geologic timescales. While the concept of vast hollow regions is not accepted in mainstream geology, the idea that substantial low-density domains might form, persist, and influence mantle dynamics is plausible within current models. Such domains can redirect heat flow, affect deep convection patterns, or trap ancient materials, altering everything from surface volcanism to magnetic field behavior. Still, turning raw seismic variation into specific geological models requires further, corroborated data. That need for replication and cross-check drives plans now being discussed among oceanographic and seismological teams. Controlled source experiments, where known energy pulses are generated and observed across multiple stations, could help distinguish between density changes, compositional layers, and other factors contributing to the anomaly. These efforts demand significant coordination and resources, deploying or servicing instruments at extreme depths, and aligning measurement campaigns across international networks. Yet they represent the most direct way to test whether recurring wave patterns are artifacts of measurement, byproducts of ordinary mantle variation, or actual signatures of unusual zones. Even without a definitive answer, the episode underscores how advances in detection change the scope of what scientists can observe. Signals that once blended into background noise can now be examined in enough detail to invite complex hypotheses. A decade ago, the same waveform might have been dismissed as statistical clutter. Today, it can become the subject of modeling, interdisciplinary workshops, and targeted expeditions. The end result is a richer, if more complicated, image of a planet whose deep architecture is still only partially understood. As global seismic networks continue to expand and incorporate more sophisticated analysis tools, the ability to compare and cross-check data from varied environments will improve. Whether anomalies like this resolve into confirmed structures or dissolve into recognized background variation, each investigation contributes to better mapping of the forces and materials at work beneath the surface. The current Pacific case joins a small library of such puzzles. Events that, while carefully anchored in observable data, invite multiple plausible explanations. And while these observations come from kilometers down in the mantle, the same analytical mindset is being applied much closer to where people live and work. In settings where direct access is possible, researchers have the advantage of pairing remote sensing with on-the-ground verification. That combination has recently been applied in environments far removed from the open ocean, using a different kind of sensing technology that can detect voids and structures invisible to surface mapping. Ground-penetrating radar sees what maps cannot. In early 2025, urban survey teams in several countries began integrating a new generation of ground-penetrating radar into their work, systems adapted from designs once used for specialized military and geological applications. Unlike earlier civil models, these arrays combined multiple antennas, adjustable frequencies, and improved signal processing to produce clearer images at greater depths. They could send pulses through dense substrates and return high-resolution, three-dimensional representations of subsurface features, even in environments cluttered by utility lines, reinforced concrete, and compacted soil layers. Initially, these advances were applied for straightforward engineering tasks, assessing the stability of building foundations, identifying voids that might become sinkholes, and finding aging infrastructure before it failed. But as deployments expanded, surveyors began to log anomalies with shapes, patterns, or positions that did not correspond to existing records. Some presented as long, straight alignments beneath layers of natural rock. Others emerged as clusters of reflective surfaces arranged with symmetry uncommon in natural cavities. These returns did not automatically signal human origin, but they stood apart from the irregular voids caused by erosion, lava flow, or frost cracking. In dense urban districts, unexpected findings carried both practical and historical implications. Unmapped openings below street level could introduce engineering risks, but they also hinted at past construction or geological features that had gone undocumented until now. Public works departments, from North America to South America, commissioned follow-up surveys in zones where signal echoes persisted after repeated passes. While most revealed prosaic explanations, abandoned service tunnels, obsolete storm drains, others remained unresolved, lacking any match in archives or known geology. Engineers approached such cases cautiously. Single-method detection, even with high-grade radar, can be misleading. Moisture content, mineral composition, and angular rock contacts can all distort a return to make it appear more regular than it is. As a result, current best practice is to corroborate with other methods such as borehole inspection, gravity surveys, or seismic readings before assigning any interpretation. If structured patterns are confirmed, plausible explanations might range from rare ancient mining layouts and modified natural cavities to uncommon geological formations with unusually consistent geometry. Each scenario would carry different implications, and each would require direct sampling or visual confirmation before further conclusions. A recurring advantage of the latest systems lies in their ability to adjust in real time. Operators can change pulse frequency to penetrate different materials or focus on specific depth bands, filtering out interference from overlying structures. This adaptive approach, described in recent IWAGPR and MDPI reports, has reduced ambiguity in complex conditions such as layered bedrock overlain by fill. In effect, it allows a surveyor to tune the scan to avoid unwanted reflections, much like adjusting a lens to focus on one layer in a stack. In several 2025 projects, this capability enabled imaging beneath earlier tunnels or basement levels without those nearer features obscuring the view of deeper strata. In one European capital, city planners extending a transit line used the arrays to rule out hidden cavities at the planned tunnel depth, only to find unexplained voids 20 meters below that level instead. In Southeast Asia, an expansion of drainage works revealed reflective patterns under a coastal district that did not align with mapped piling foundations or sea defense works. Both cases remain under study, with teams weighing possible human utility against natural origins. These examples underline a broader point drawn from current research. Radar alone can point to anomalies, but understanding their nature demands multiple lines of evidence. TerraProbe's own urban surveys emphasize integrating 3D radar imaging with targeted drilling, temperature profiling, and in some instances, micro-robot probes for direct exploration. Reducing reliance on a single data type helps avoid misinterpretation and ensures that resources go towards sites with the highest confidence of yielding verifiable results. In practice, many anomalies resolve into familiar categories. An apparent hole might turn out to be an abandoned shaft partially collapsed, its straight edges preserved by the surrounding rock. A reflective floor could be a dense mineral layer bounding a natural void. Still, technological gains are shifting the threshold for what can be detected and at what depth. A decade ago, features more than a few meters below a city street were often invisible to municipal surveys. Now, with synchronized multi-antenna arrays and stronger computing power, operators can assemble continuous depth profiles across large, built-up areas. The pace of adoption has grown as engineering firms recognize the value of maintaining subsurface data alongside above-ground GIS systems. Urban plans now increasingly factor in not just where surface structures will stand, but what lies beneath them over tens of meters. That shift can prevent costly overruns from encountering unexpected conditions mid-project, but it also produces datasets that, if shared, can illuminate patterns across districts and even across cities. Peripheral anomalies found in different surveys might, after collation, trace an overlooked geological boundary or an undocumented historical work. In some municipalities, policies remain unsettled on how to handle completely unexplained returns. Publishing detailed maps of certain features could attract unauthorized entry or disturb fragile archaeological remains. At the same time, withholding data complicates scientific study and public engagement. This tension between security, preservation, and transparency is becoming more visible as the capability to detect hidden features improves. Researchers working with cultural heritage authorities have suggested tiered data releases, enough detail to support academic and engineering use, with sensitive specifics held until sites can be assessed for stability and significance. From a research perspective, the most intriguing class of finds remains the structured echo, returns that maintain consistent shape across multiple passes and vantage points. While rare, these patterns draw interdisciplinary teams willing to combine radar with high-resolution gravimetry, magnetometry, and in some cases, endoscopic imaging through narrow boreholes. The goal is to understand whether the structure is best explained by geology, human intervention, or a blend of both. Unusual formations like polygonal basalt columns or certain crystallized mineral bodies demonstrate that nature can produce regularity. Conversely, ancient builders often leveraged natural features to minimize excavation. The only certainty is that without physical access, assumptions risk outpacing evidence. At the international level, conferences like IWAGPA 2025 have showcased urban case studies alongside advances in hardware and software. Prototype drone-mounted radar, for example, aims to map hazardous collapse zones from above without risking crew on unstable ground. Integration with AI-driven classification software can sift vast image sets, highlighting areas whose subsurface returns match chosen criteria, whether linear alignments suggestive of transport works or amorphous pockets matching karstic voids. The same imaging principles extend beyond city cores. Infrastructure corridors, heritage sites, and post-industrial landscapes all stand to benefit from the ability to see beneath the visible layer. As datasets grow, patterns may emerge that link anomalies across environments, hinting at larger systems or repeated engineering solutions over time. Incremental mapping in this way avoids the cost and risk of deep excavation, while steadily improving the model of what lies below. Yet the deeper philosophical and policy questions remain. The capacity to detect hidden cavities, tunnels, or chambers raises debates about ownership of the space below private property, the right to excavate, and the responsibility to preserve. These considerations become sharper when the structure lies beneath populated districts, where the public has a direct stake in both safety and heritage. For scientists and engineers, each unexplained echo is both an opportunity and a dilemma. Pursue the answer and risk disturbance, or leave it untouched, perhaps indefinitely. As 2025 unfolds, more cities are commissioning the kind of broad, multi-layer scans once reserved for select engineering projects. The resulting composite images show that urban space is not just vertical in the visible sense of towers and basements, but vertical in a much deeper, more complex way. Beneath the mapped infrastructure lie layers of altered ground, legacy excavation, natural cavity, and, in rare cases, forms whose symmetry resists easy classification. These developments invite a public conversation about how much of the invisible city should become visible. What do cities hide beneath their feet? And who decides if we should find out? Such questions will only grow sharper as attention shifts from single anomalies to entire hidden networks, some of which were meant to support life beneath the surface. Modern underground cities you've never heard of. Across different regions, there are places where what lies beneath the surface is not just service tunnels or isolated basements, but entire built environments designed for human occupation. Some have been in use for centuries. Others are recent or still in progress. Archaeological records confirm that certain ancient societies invested immense effort into underground construction, producing multi-level settlements capable of sustaining large numbers of people. Cappadocia in central Turkey remains one of the most studied regions in this regard, with complexes like Derinkuyu and Kemokli showing that deep, self-contained cities were not only possible but were maintained over long periods. These structures descend dozens of meters and contain interconnected chambers, ventilation shafts, water access points, and defensive features, all cut by hand into volcanic tuff. Renewed interest in how such cities were built and maintained is being shaped by advances in survey and exploration tools. In recent years, small robotic platforms and remote sensing arrays have been tested in complex cave systems worldwide. These devices, some the size of a compact power tool, are able to traverse narrow or unstable passages while sending back sensor data and imagery in real time. While much of the work takes place in natural cave settings, The same technology can be applied to archaeological sites that have blocked or dangerous sections. This approach does not confirm specific new extensions in known sites, but it is steadily adding detail to existing maps and making it more feasible to investigate sections that human teams cannot safely reach. The persistence of these large underground spaces in the archaeological record has led some researchers to revisit their possible functions. Protection from hostile forces, environmental stability, and the ability to control access to resources all appear in different case studies. In Cappadocia, connecting tunnels between complexes suggest the possibility of coordinated refuge across settlements. Ventilation systems that still function today indicate a sophisticated understanding of airflow management, even if the precise construction techniques remain under study. These features are not unique to one site, but recur in other large subterranean works built in regions with extreme weather, scarce resources, or periods of instability. The modern equivalents are planned with different materials and tools, but the reasoning has familiar elements. In multiple countries, urban planners are looking at underground expansion not simply for transport and utilities, but as viable space for commerce, housing, and public life. Reports on the growth of technical surveying communities and the cave diving and exploration sector show a parallel uptick in civil engineering projects making use of similar scanning and mapping technology. The same radar systems and sensor arrays that help document archaeological sites are proving useful in selecting and monitoring construction zones beneath cities. Climate resilience is a major driver. With heat waves, severe cold snaps, and extreme weather becoming more common, building below ground offers a way to maintain controlled environments year-round. Several metropolitan areas are studying or implementing expansion of their existing subterranean networks for this reason. These are not narrow service corridors, but connected districts designed for pedestrian movement, commerce, and gathering, linked to surface transport hubs. Excavation methods vary by geology, but the goal is to create stable, insulated spaces that can function both as everyday connectors and as shelters during environmental stress. In older underground cities, natural insulation from the surrounding rock kept temperatures relatively constant. In modern construction, climate control systems take over that role, with insulated walls, automated ventilation, and air quality monitoring built in from the start. Airflow in ancient sites relied on vertical shafts placed to take advantage of temperature and pressure differences across the terrain. Now, electrically driven fans and smart controls manage circulation, adjusting for occupancy and conditions in real time. The principle, fresh air must reach every occupied level without pockets of stagnation, has not changed, but the means of achieving it have. Water sourcing offers another parallel. Archaeological evidence shows that underground cities often tapped aquifers or stored rainwater in cisterns protected from surface contamination. Modern developments incorporate water storage and purification to ensure self-sufficiency if supply lines are interrupted. While the technology now involves pumps and filtration membranes, the objective remains the same: secure water inside the structure itself. Engineering constraints also echo across time. The deeper the structure, the higher the load from the overlying material, and the more carefully the excavation must be shaped and reinforced. In ancient rock-cut cities, deeper chambers tend to be smaller and more structurally conservative than those above. In contemporary projects, floor spacing, column placement, and material choice are calibrated to balance usable space against stability. Geotechnical surveys inform where excavation is possible, and monitoring systems track shifts or stress over time. These practices ensure long-term safety, just as ancient builders adjusted their layouts according to what the ground could support. Integration with the surface remains important in both ancient and modern examples. Historic underground cities often featured multiple discrete access points, including hidden or narrow shafts, to allow movement of people and goods without exposing the whole population to danger. In today's urban networks, frequent and accessible connections to surface streets, public transit, and adjoining buildings are essential for daily flow. In either case, subsurface and surface are planned as parts of the same inhabited environment, not isolated zones. One of the challenges in interpreting ancient underground cities is determining how they were constructed and expanded without modern machinery. Cut marks, tool remnants, and debris deposits provide some clues, but methods for reinforcing ceilings at depth or maintaining air quality while excavating remain topics for investigation. These questions can be approached through experimental archaeology or by applying current engineering models to the dimensions and geology of the existing spaces. Sensor data from modern instruments deployed in older structures can help quantify airflow, structural stress, and other factors, creating testable scenarios for how ancient systems might have been built and maintained. Modern projects benefit from detailed geological mapping before excavation, allowing engineers to avoid unstable zones altogether. Redundancy is built into both structure and systems. Multiple access points, backup power for ventilation, and alternate water and waste channels. These precautions echo the redundancies seen in their ancient counterparts, though framed through modern safety codes and urban planning requirements. The broad parallels suggest that when surface conditions drive people underground, whether for defense, climate, or other pressures, the resulting environments must meet consistent human needs. Shelter, breathable air, drinkable water, security, and integration with daily activity all appear as recurring priorities. The differences lie in the scale achievable, the speed of construction, and the materials available at a given time. Natural rock may give way to reinforced concrete, hand-cut stairways to elevators, but the underlying design logic stays recognizably similar. Looking at both kinds of sites side by side reinforces that subterranean architecture is not an anomaly of the past or a futuristic experiment, but a recurring form of settlement that adapts to the limits and challenges of its era. Archaeological studies deepen our understanding of what was possible with limited tools, while modern engineering shows how those same basic requirements can be met using current resources and constraints. This recurring pattern is encouraging some researchers to think more broadly about underground spaces, not just in human history on Earth, but in planetary science more generally. If certain design solutions appear again and again where humans build below the surface, and if large hollow or low-density zones can persist inside a planet's crust, then the principles gained from one field might inform investigations in another. The tools and approaches used to map hidden layers here could be adapted for environments far beyond our own world, where the unknown lies beneath a very different kind of surface. NASA's Planetary Formation Clues. In late 2024 and into 2025, a joint NASA-ESA initiative set out to compare the internal architecture of different planetary bodies, using orbital instruments to map more than just their surfaces. The focus was on layered datasets, high-resolution radar images, gravitational field measurements, and topographic correlations that could reveal how the crust and upper mantle vary in structure and density. Spacecraft in orbit around Mars and Ceres supplied most of the data. When processed, these measurements highlighted zones where mass distribution departed noticeably from surrounding rock, producing what researchers classified as low-density anomalies. In their most basic description, these were regions where the material beneath the crust seemed lighter or more irregular than expected in a stable, uniform shell. Interpreting these anomalies is not straightforward. The data cannot directly resolve empty cavities in the way a camera shows a picture. Instead, the lower densities and unusual radar returns are patterns that can be consistent with a number of possibilities. Fractured rock, unconsolidated material, layers rich in volatiles like ice, or in some cases complex networks of internal voids. The planetary science teams emphasized that the same anomaly could have different causes depending on local geology. What the results did make clear was that substantial subsurface complexity exists on both Mars and Ceres, and that it can be mapped over large areas when combining multiple orbital sensing techniques. On Mars, several of the low-density areas appeared within ancient volcanic provinces such as Tharsis, regions thought to have undergone immense magma movement in the planet's past. These volcanic landscapes have long been associated with structural weaknesses, lava tubes, and collapse features, so the idea that some of the anomalies here might relate to old magma chambers or volatile altered rock is plausible. In some radar profiles, the scattering patterns could be read as signs of embedded cavities or lighter layers sealed beneath more solidified flows, but the exact internal geometry remains uncertain without direct sampling. Series presented a different pattern. There, some anomalies correlated with surface depressions and dome-like structures linked to ideas about ancient cryovolcanism, geological activity involving water and other volatiles instead of molten rock. Certain depressions are situated above zones where gravitational mapping suggests lower subsurface density. Scientists note that these could be relic chambers where ice, salts, or other volatile materials once existed before migrating or dissipating. But interpretations vary. Fractured crust, porous material, or compositional differences could also produce the signal. The evidence is consistent with past volatile activity, but it does not lock in a single structure type. Underlying many of these discussions is the concept of volatile outgassing, the release of compounds like water, carbon dioxide, ammonia, or methane from a planet's or moon's interior as it cools and evolves. When such materials are trapped within the crust, changes in temperature and pressure can cause them to expand or shift phase, forcing pathways through surrounding rock or ice. As volatiles escape, they can leave behind zones of reduced density. If subsequent geological activity does not infill these spaces, they may persist for long periods, buried beneath younger layers. The mechanics of this process are general. Whether the volatile material is water ice in cryovolcanic terrain or gas coming out of silicate melt, the expansion and migration can generate low-density regions that are detectable through their gravitational and radar signatures. The actual size, shape, and longevity of such features depend on the planet's heat flow, crustal composition, and tectonic history. Studying them in the relatively well-preserved crusts of Mars or Ceres helps scientists refine models for how they might appear elsewhere. For Earth, the analogy lies in the underlying physics, not in a direct duplication of planetary features seen from orbit. Our planet's restless geology, hydrological cycle, and erosion erase or distort much of the original crust record. Yet in very old and stable regions, like cratonic shields, there may be deep structures that have remained relatively undisturbed for hundreds of millions of years. If these areas once contained volatile-rich zones that were sealed before their contents fully vented, they could, in theory, preserve some measure of their original low-density character. Applying methods proven in planetary studies to Earth is challenging. Our planet's gravitational field is influenced by oceans, atmosphere, and the mass of mountains and trenches, all of which add noise to readings. Still, advanced gravity mapping, gravity gradiometry from aircraft or satellites, can detect subtle mass anomalies at depth, especially when combined with ground-based seismic or radar surveys. Researchers cited recent MDPI papers on ground-penetrating radar in planetary applications as directly relevant here, noting how signal processing techniques adapted for Mars or lunar missions can improve subsurface imaging on Earth. By matching patterns from planetary anomalies to terrestrial survey results, scientists hope to better target areas for follow-up investigation. This means looking at a combination of factors: crust type, history of volcanic or intrusive activity, known fault structures, and records of deep seismic irregularities. Where several of these indicators overlap, the probability of encountering a preserved low-density formation rises. In a few early mapping trials, some Earth regions with unexplained gravitational or seismic signatures have shown pattern similarities to particular Martian or Sirian anomalies. These similarities are intriguing but remain hypotheses until verified by more direct evidence. The comparison work also extends to thinking about how such features might evolve over time and what they could contain. On Ceres, for example, spectroscopic analysis has identified salts associated with certain depressions, leading some to propose that brines once moved through connected underground spaces. On Mars, later volcanic episodes may have partially filled earlier voids with minerals. If Earth hosts analogous structures, some may have remained sealed and chemically isolated for vast spans of time, potentially preserving unique fluid or gas compositions. This perspective adds another layer of interest, connecting what begins as a structural question to broader geochemical and even biological considerations. Planetary formation research shows that the creation and burial of void-like regions within a crust is a common outcome of early geothermal and geochemical processes. The scale and persistence differ between worlds, but the essential drivers, volatile release, thermal contraction, compositional heterogeneity, can be found in many planetary contexts. On Earth, plate tectonics complicate the survival of such features, but certain structural settings might protect them instead of destroying them, folding or sealing them beneath layers of more stable rock. A useful reminder of why subsurface features matter comes from a very different field study. Gina Moseley's work in Greenland's remote ice caves and the speleothems they contain. Those mineral formations preserve chemical records of climate change over hundreds of thousands of years. By analyzing them, scientists reconstruct past environmental conditions far beyond the reach of written history. The analogy is straightforward. Whether in rock, ice, or mixed materials, enclosed and stable spaces within a planet can act as long-term archives, holding information that surface processes would otherwise erase. From a technical perspective, linking planetary science to terrestrial geology is still relatively new. The 2025 NASA ESA mapping campaign marked one of the first intentional efforts to assemble a reference library of structural patterns from multiple worlds and then see how those patterns might inform surveys here. By cataloging how low-density anomalies associate with specific surface expressions or geological settings elsewhere, researchers strengthen their ability to interpret Earth data that might otherwise be dismissed as noise. The gravity and radar maps of Mars and Ceres now serve as comparative templates. As imaging and measurement of Earth's interior improves, these external reference points can act as a check on our interpretations. A seismic pattern here that aligns with a well-characterized anomaly type on another planet may warrant deeper scrutiny. Over time, the reciprocal relationship between planetary exploration and terrestrial surveying could clarify how common large, stable low-density structures truly are inside planets, and what range of forms they might take. That possibility has implications well beyond day-to-day geology. It touches on long-standing questions about the scale and nature of the spaces that can exist beneath a planet's surface, and whether some of them could remain viable over geological time. Recent discussions among geologists and planetary scientists suggest that rethinking the size, stability, and distribution of such formations may change how we talk about certain long-debated ideas. The way those concepts are framed is beginning to evolve, shaped less by speculation and more by a growing body of comparative evidence. The hollow planet theory gets a scientific reframe. In 2025, scientists addressing ideas once grouped under hollow Earth began using a different framework. For much of the last century, that label implied a single, continuous empty space inside the planet, an image long dismissed in geological literature and in fact checks as incompatible with established models of Earth's layered interior. The new conversation focuses instead on something more limited and testable: localized, long-lived low-density zones, sometimes called megacavities. In this context, the term refers to large voids or networks of voids within the crust or upper mantle, formed by natural processes and confined to specific regions, not an interconnected hollow sphere. This shift has origins in decades of subsurface data that showed the planet's interior was not perfectly uniform. Seismology, gravimetry, and radar mapping have identified areas where density appears reduced compared to surrounding rock. On other worlds, similar low-density anomalies have been confirmed to correspond with preserved hollow structures, such as ancient lava tubes or cryovolcanic chambers. On Earth, the match is less concrete. Most anomalies at depth are interpreted as fractured or partially molten rock. Still, Improvements in resolution and modeling make it possible to consider that some may be spaces with significant void content. Because direct confirmation is lacking, researchers now frame the idea in terms of scientific testing rather than proof of a hidden inner world. Recent seismology work, reported in venues like Nature Geoscience and by researchers such as John Vidal, demonstrates how advances in deep Earth imaging are revealing greater complexity. These studies show the inner core may rotate at varying speeds over decades, and that seismic waves behave in nuanced ways depending on path and depth. Work like this illustrates how models are refined as new data appears. Features once invisible can become measurable, and geological processes once treated as uniform are shown to be variable. By analogy, zones of unusually low density can be analyzed in more detail than was possible a generation ago, making it practical to define what would constitute a megacavity and where such features might physically exist. Mechanisms for their formation are not speculative inventions, but extensions of known geological processes. On planetary bodies from Mars to Ceres, cavities have been associated with volcanic outgassing, crustal deformation, and the sealing off of lava flow systems. In some models, mineral precipitation along roof and wall surfaces acts as reinforcement over time, similar to arch-like supports. On Earth, sealed pockets from ancient outgassing events, if protected from major tectonic activity, could, in theory, persist far longer than the shallow caves we explore today. The same physics that creates low-density zones around volatile-rich regions elsewhere in the solar system can apply here, adjusted for our higher gravity and more active crust. Simulations and rock mechanics studies support the plausibility that irregularly shaped voids might survive at depth if stress is distributed through denser surrounding layers. Rather than picturing an open sphere, the models suggest configurations of chambers, pillars, and reinforced vault-like spans. Heat from the surrounding rock could stabilize at near-constant levels in sealed systems with no fluid exchange, and gases trapped during their formation could persist. These conditions would be rare, occurring beneath geologically quiet crust, but they are not beyond what the physics allows. The reframed concept gains traction because it avoids the universal instability problem of a planet-wide empty shell. Localized structures can be assessed case by case, with size and longevity depending on local composition and tectonic history. This makes them approachable with the same tool sets used in mining exploration, geothermal assessment, and earthquake hazard mapping. It also avoids the pseudoscientific baggage that Hollow Earth carried, encouraging participation from geoscientists, planetary researchers, and engineers who can test the idea within the bounds of established methods. In practice, most scientists debating the size and depth limits recognize strong constraints. Rock becomes more deformable under high pressure, and at certain depths only very strong crystalline compositions or ongoing mineral deposition could prevent collapse. Estimates for the maximum span vary widely, from a few kilometers across in active crust to potentially larger in the most stable continental interiors. The important point in the current framing is that not all real estate beneath our feet has the same potential for harboring such spaces. Detection, if it occurs, will rely on multiple methods. Seismic studies can look for delayed and scattered wave arrivals that might indicate large low-density regions. Satellite and airborne gravimetry can spot subtle dips in local gravitational pull. Ground-penetrating radar has limited depth range in rock, but when paired with downhole sensors, it can help connect shallow expressions to deeper anomalies. The technologies described in recent MDPI and planetary exploration papers, including inversion methods to model shapes from incomplete data, are part of this growing toolkit. One advantage of tying the discussion to comparative planetology is that known examples on other worlds can serve as references. Mars, with its vast volcanic provinces, preserves enormous tubes and chambers thanks to its lower gravity and lack of plate tectonics. Ceres has cryovolcanic features that suggest subsurface chambers persisted beneath volatile-rich plains. Such analogues help set expectations for what might be possible on Earth under the right conditions, while highlighting that more active geology here makes their survival less likely, and therefore more interesting if found. For researchers developing the megacavity concept, the objective isn't to validate myths of civilizations inside the planet. It's to integrate an underexamined structural category into our picture of the subsurface, using measurable, physical criteria. We already accept that giant cave voids exist near the surface, and that more complex, low-density zones exist deeper down. The open question is whether some of those deeper zones meet the structural requirements to be categorized as true megacavities. Exploring that question does not require discarding fundamental geophysics. It requires applying them to a slightly broader range of possibilities than before. Different disciplines now participate in that exploration. Structural geology helps define where rock strength and stress patterns would permit large, unfilled spaces. Seismology analyzes regional wave patterns for consistency with modeled voids. Planetary science adds context from other bodies. Even climate science weighs in, noting that large underground structures could influence geothermal gradients and long-term environmental stability above them. Bringing these approaches together emphasizes that the discussion has moved into a testable research space rather than speculative storytelling. In academic talks and technical papers, it is becoming clearer that replacing hollow Earth with megacavity is not just a change in terminology, it's a change in how the problem is posed. The former conjures an unbroken void and the baggage of conspiracy. The latter describes a class of formations bounded in size, distribution, and cause, and open to falsification through evidence. This reframe keeps the conversation grounded in measurable data and makes it clear that the stakes are scientific. Understanding how large natural cavities form, persist, and interact with their surroundings, on Earth and elsewhere. The outcome of such work could add a new category to the catalogue of geological structures we recognize, joining lava tubes, karst systems, and glacier moulins as features of interest in both geology and planetary science. Even if the largest megacavities prove smaller or rarer than some models allow, refining the search parameters will improve our understanding of the subsurface as a whole. It will also clarify the conditions under which isolated and stable zones can exist at depth. Those conditions carry implications not only for physics and geology, but also for something else scientists are increasingly considering: what might be able to live there, if such environments are real. Life down there. Biological mysteries from subsurface expeditions. In recent years, scientific expeditions into some of the world's least accessible caves have been uncovering ecosystems that challenge long-held assumptions about where and how life can persist. In 2025, several previously isolated sites were surveyed with the specific aim of cataloging biological communities adapted to complete darkness, stable extreme conditions, and unusual chemical settings. These expeditions, building on work in places such as Bhutan's vast karst passages and Mexico's deep limestone systems, are showing that the subsurface can host complex and highly specialized life, much of which has never been seen before. One study team from Northern Arizona University, working in the high-altitude caves of Bhutan, reported finding dozens of arthropod species new to science. These invertebrates had adapted to perpetual night with traits such as loss of pigmentation, elongated appendages for navigating narrow fissures, and heightened non-visual sensory perception. Their survival depended on a mix of imported surface nutrients, washed down during seasonal rains, and chemical energy sources within the cave itself. While some species fit known cave-dwelling archetypes, others showed unexpected behaviors, exploiting microhabitats where mineral deposits or water chemistry created distinct niches within meters of one another. Elsewhere, BBC documented research in cave systems like Sierra Juarez and the submerged passageways near Wuki Hole offered parallel lessons. Microbial mats in certain chambers were found to derive their energy not from sunlight, but from oxidizing minerals in the rock or interacting with chemical compounds carried in seepage water. These chemoautotrophic pathways are well known in hydrothermal vents under the ocean, but their presence deep inland underscores how biological communities in darkness can run entirely on geological inputs. The precise mineral energy combinations vary from site to site: sulfides, nitrates, ferrous iron, but the result is the same: a self-sustaining biochemical loop independent of the surface photosynthetic cycle. This mode of survival has a broader significance. In the absence of sunlight, most surface-based ecosystems collapse quickly without an external energy source. Caves, however, can develop isolated chemistries that allow microbial life to flourish for centuries or longer, independent of seasonal change or climate disruptions above. These communities often become the base of small but diverse food webs, biofilms feeding tiny grazers, which in turn support predators, all compressed into a few cubic meters of habitable space. In the Bhutan and Sierra Juarez sites, camera traps and slow observation techniques have captured small crustaceans, blind fish, and troglodytic insects interacting in ways familiar to ecologists, but in worlds sealed off from day and night. Some sites exhibit even more unusual environmental makeups. Pockets where groundwater interacts with certain mineral veins produce gradients in pH or trace gas content that appear to define sharp habitat boundaries underground. Researchers in Mexico noted that a chamber's ceiling might support one specific bacterial community, while just meters away, a pool on the floor housed an entirely different network of organisms. These boundaries are dictated not by temperature or light, but by chemical availability, making them valuable natural laboratories for studying how microenvironments drive evolution and diversification. One characteristic recurrent across such expeditions is the high proportion of organisms with no close matches in genetic databases. The lack of comparison points makes it difficult to assess how long these communities have been isolated, but in many cases they contain genetic markers consistent with long-term adaptation to extreme and unchanging conditions. Without claiming precise timelines, scientists can say with confidence that these adaptations arise from many generations spent in stable but challenging settings, where energy must be extracted efficiently from limited chemical resources. For microbiologists, this raises important questions about the range of metabolisms possible in Earth-like conditions. While photosynthesis is dominant at the surface, underground life often uses oxidation-reduction reactions involving sulfur, iron, or manganese compounds, sometimes with unexpected byproducts. In certain hydrogeologically active areas, these reactions could produce trace amounts of oxygen or other oxidizing agents, even in the absence of light. While such processes operate on a smaller scale than surface systems, in confined environments they may be sufficient to support multi-tiered communities. These findings also draw interest from planetary science. The principle that life can function without sunlight, subsisting entirely on geological energy, applies directly to environments we suspect exist elsewhere. Mars has subsurface deposits of sulfates and perchlorates. Icy moons like Europa and Enceladus likely have oceans in contact with silicate beds under high pressure. If chemical reactions between water and rock can sustain life in terrestrial caves, they might do the same in alien settings, all without any photosynthetic input. The comparison runs in both directions. Studying how cave systems maintain chemical stability over long periods helps refine models for extraterrestrial habitats. National Geographic's work in Greenland, for instance, demonstrated that mineral formations in ice caves can lock in environmental records for tens of thousands of years. Similarly, rock-hosted microbial communities in remote caves may preserve chemical snapshots of past conditions, showing how life has tracked environmental change entirely sheltered from UV radiation and surface weather. Such snapshots could be critical analogues for interpreting data returned from missions to other planets and moons. Back on Earth, these cave ecosystems also have implications for our own planet's history. Periods of extreme cold or atmospheric disruption have punctuated geological time, during which surface ecosystems suffered collapses. Sealed subsurface systems could have served as refuges, maintaining pockets of biodiversity that would later recolonize the surface. Some researchers hypothesize that during events like the cryogenian glaciations or post-impact winters, chemically powered communities in caves and aquifers might have been critical to the persistence of certain lineages. While direct fossil evidence for such refuges is sparse, the survival strategies seen in modern cave life offer plausible templates for how this could have occurred. Exploring these environments is logistically challenging. Access often requires negotiating narrow, unstable passages, or diving through submerged conduits with no natural light and unpredictable currents. Teams employ protocols designed to prevent contamination in both directions, protecting fragile local ecologies from human-introduced microbes and ensuring retrieved samples are uncontaminated for laboratory work. Strategies include sterile sampling kits, sealed transfer containers, and in situ measurements to record environmental parameters before the sample is disturbed. What emerges from these controlled studies is an appreciation of just how varied and site-specific subsurface life can be. Even within a single cave, communities in separate chambers may operate on different energy chemistries, with no direct biological overlap. Detailed mapping of such variation is now a priority, as it can point to underlying geological processes, fault lines, mineral intrusions, or groundwater flow paths that structure life's possibilities in the absence of sunlight. Some expeditions extend their surveys to environmental DNA floating freely in water or sediment, revealing organisms never directly observed during fieldwork. Traces of multicellular life, worms, crustaceans, or small fish, appear in sequences alongside the microbial dominants, suggesting more complex assemblages than camera observations alone would imply. Although biomass levels are low compared to surface waters, the interconnected roles within these food webs are clear, with geochemistry at their foundation. Understanding how such systems persist is not purely academic. Chemically powered ecosystems, once established, can operate independently for prolonged spans, potentially centuries or millennia, as long as geological inputs remain stable. This endurance has obvious parallels to the aims of closed-loop life support systems in space exploration, where light and surface-like conditions cannot be assumed. The organisms thriving in deep, dark caves are, in effect, naturally occurring versions of what engineers try to replicate in spacecraft and extraterrestrial habitats. Because of these links, isolated subsurface ecosystems are attracting joint interest from biologists and planetary scientists. They are seen as proving grounds for the principles of sustainable life in enclosed environments, and as case studies for what to look for beyond Earth. Every newly documented pathway for extracting energy from minerals or maintaining a food web without sunlight broadens the definition of a habitable zone. It is this combination of biological novelty, geological stability, and independence from sunlight that keeps these discoveries relevant beyond their immediate settings. Each new find in Bhutan, Mexico, Greenland, or other remote sites strengthens the case that life's adaptability is not constrained by our surface-biased view of the world. And in the broader scientific conversation, these ecosystems become more than curiosities. They are comparative models, useful in interpreting unexplained observations elsewhere. As more data accumulates, the next questions naturally turn to how similar principles might apply outside of Earth. If life can persist in the dark on chemical energy deep underground here, the search for analogues on other worlds can proceed with a clearer set of expectations. The investigative tools refined in these extreme terrestrial environments are already proving adaptable to other, more distant settings, places where direct sunlight never penetrates, but where structural and chemical conditions may be just as conducive to sustaining living systems. And some of the most intriguing signals to compare with these earthbound examples are now coming from well beyond our own atmosphere. Space missions testing the theory off-world. In parallel with Earth-based research, planetary missions are providing controlled, low-noise environments for testing ideas about what lies beneath a planet's surface. Instruments orbiting or placed on other worlds can gather seismic, radar, and gravity data without the constant background variation caused by oceans, complex weather systems, and active plate tectonics. For researchers trying to understand ambiguous signals from within Earth, these extraterrestrial datasets offer clean baselines and comparative examples for how energy moves through known materials under simpler conditions. The Moon is one of the most accessible settings for such work. Decades-old Apollo-era seismometers have already shown how lunar crust behaves under mechanical stress, recording signals from both natural moonquakes and impacts. More recent proposals build on that legacy, with expanded seismic networks positioned across different lunar regions to collect a broader range of events. In the absence of hydrological cycles or deep tectonic activity, even faint and rare waveforms stand out sharply against the quiet background. This makes it possible to observe how seismic waves scatter, reflect, or attenuate when moving through fractured rock, layers of regolith, or transitions in material density, behaviors that would be difficult to isolate beneath Earth's more active surface. Each recorded event becomes a reference point. When a wave passes through a boundary in the Moon's subsurface and produces a measurable delay or change in amplitude, researchers can track its path against models derived from orbital gravity mapping and surface geology. If the same pattern emerges consistently in similar conditions, it establishes a repeatable link between signal and structure. Bringing that knowledge back to Earth, a seismologist examining a comparable waveform can check whether the lunar example predicts similar causes here, knowing how it behaved in a simpler environment. Planetary radar studies play a similar role. Spacecraft instruments designed to penetrate below surfaces, whether of rock, ice, or mixed materials, can map internal boundaries and layers with far less signal distortion than on Earth. Icy moons, in particular, lend themselves to this kind of remote sensing. Thick ice shells transmit radar waves differently depending on grain structure, impurity content, and phase changes between ice and liquid water. When orbital passes trace these variations into a layered or irregular subsurface map, it produces a dataset for calibrating radar equipment used in terrestrial polar studies. Cases where radar signals from orbit successfully predict features later confirmed by high-resolution imaging or lander measurements are especially useful, because they show what signal patterns to expect for certain materials and depths. Europa, with its combination of surface fissures and subsurface layering, has become a focus for improving our understanding of ice-penetrating radar. Each pass of a dedicated deep structure mode can highlight changes in reflectivity that point to complex internal architecture. Some layers may be the result of seasonal or orbital heating, others from long-term circulation within the ice shell. Whatever their origin, the clarity of these features in a low-interference environment helps refine the same analytical methods applied to radar surveys of Earth's ice sheets. If a specific type of reflection in Europa's data consistently marks a change in density or composition, radar operators on Earth can interpret similar returns from Antarctica or Greenland with greater confidence. These missions, whether focused on seismic or radar studies, are united by their comparative value. Each one adds to a growing cross-planetary library of subsurface signals and their likely sources. The Moon demonstrates how seismic waves behave in solid silicate crust untouched by water or continuous convection. Europa and other icy bodies show how radar pulses map stratified and potentially mobile ice layers under extreme cold and pressure. Because the environments and materials are more consistent than on Earth, patterns in these datasets are easier to define, and those patterns can then be applied to more complex cases at home. The process does not rely on finding exact matches between signals from different worlds. Instead, it looks for transferable principles: how a given wave responds to a density change, how a reflection strengthens or weakens across an interface, how background conditions alter the clarity of a return. In this way, signals seen on other worlds become test cases for interpreting Earth's mixed and noisy signatures. Through repeated comparison, the range of plausible explanations for any one anomaly can be narrowed. An important part of this approach is the deliberate pairing of multiple sensing techniques. On the Moon, seismic readings can be correlated with orbital gravity data to match wave behaviors to specific mass distributions. On icy moons, Radar profiles can be compared with surface imaging and thermal maps to connect reflectivity changes with heat flow or fracture patterns. When more than one method agrees on the location and nature of a boundary, the case for that interpretation becomes much stronger, and that combined method can then be used wherever similar measurements are possible. For Earth science, the benefit is in clearer understanding of how to read subtle or ambiguous features. A strange seismic echo in a terrestrial dataset might be due to a hidden cavity, a change in rock composition, or an area of intense fracturing. Knowing how each of these possibilities looks in a less complicated planetary environment helps assign probabilities and design follow-up studies. Some cases might prompt targeted drilling or more focused ground-penetrating radar sweeps. Others might be set aside as unlikely to yield significant results, saving resources for more promising sites. This cross-planetary calibration is still in its early stages. Most worlds beyond Earth are only partially mapped below their surfaces, and the instruments we send have to balance many competing mission objectives. Still, every additional seismic station, radar pass, or gravity survey adds another point of comparison. Over time, these points form patterns that bridge planetary science and geology, linking the known to the unknown in both directions. By using the simpler environments of the Moon, icy moons, and other target worlds, scientists can refine the tools and analytical models used to probe Earth's internal structure. The comparative method transforms isolated signals into parts of a larger framework, where origin, material, and boundary effects are better understood. It is a cautious process, grounded in repeatable measurements, but its potential reach is significant. In both planetary and Earth science, understanding subsurface architecture matters for more than curiosity. It can reveal the history of impact events, trace past flows of water or magma, and identify regions that have remained stable for billions of years. In some cases, it may point to settings where life, microbial or otherwise, could endure. The cleaner the signal, the better our chances of reading that history accurately. By connecting what space missions learn from other worlds to the study of our own, researchers expand the limits of what can be inferred without direct access. Each confirmed feature off-world adds a trusted reference in our catalog, shaping how we evaluate anomalies here. Seen this way, every orbital pass and surface sensor network becomes part of a single, long-term experiment to map the hidden terrains of planetary bodies. And as these comparative maps develop, they set the stage for reconsidering what we think we know about the structure beneath our feet, and how much of it remains unmapped. In 2025, advances in ground-penetrating radar, multi-channel seismic arrays, and coordinated exploration have revealed that the planet's interior is more varied than the once simple models of solid rock layers suggested. From documented natural caverns sealed for millennia to newly charted subsurface networks beneath populated areas, verified case studies are expanding what scientists can measure and map. Comparative work with planetary datasets is adding further context, showing how similar processes shape other worlds. Taken together, 2024 to 25 has shifted the question from whether such structures are possible to assessing their scale and importance. If you found the J2 cave dives, Greenland ice cave data, or recent GPR breakthroughs most surprising, share your thoughts below and consider subscribing to follow evidence-driven updates as this record continues to grow.